Afternoon. Click the got it. All right. Yeah, welcome to this ARM webinar on ArcticShark Uncrewed Aerial System data. My name is Beat Schmidt. I'm the manager of the ARM aerial facility, and you'll be hearing from me first. Here is, all right. Yeah, so here is what you'll hear today. I'll start by giving you an overview of the ArcticShark program, talk about recent deployments, and then talk about the upcoming call for user proposals to actually use the ArcticShark. That will be followed by Van May talking about mid-size UAS data available through data discovery. And then we're going to launch into a series of small, short presentations on science examples. You can see the titles there: Van May, Swaroop, Jizang, Jerry, Jason, and Hailong will show these science examples. And yeah, I like the singing. All right. Okay, so let's get going on this overview. So many of you may have seen this slide before. This is just the technical specifications of the platform we're talking about. The ArcticShark has a wingspan of 22 feet, length a little bit over 14 feet, empty weight 427. The maximum takeoff is 650. Most importantly, that allows us up to about 100 pounds payload. We're not nearly using all of that currently. It also has about 2,500 watts of available payload power for the instrumentation. We're not nearly using that at this point. It has on-the-wing hard points, meaning that's where you can attach instruments to. I think currently we're using 2 of the 4. It has a maximum published flight altitude of 18,000 feet. We have not been able to take it that high yet, but we've come somewhat close. The highest we've taken it was 15,400 feet. It has a published endurance of about 8 hours. From what we're looking at with the current payload, and we just established that recently, it looks that we may get about 6.5 hours with everything we have in and the things on the wing, which is still pretty spectacular. Flight speed is between 60 and 70 knots indicated airspeed. That's if you want a rule of thumb, if you divide knot indicated airspeed by 2, then you get meters per second. So 30 to 35 meters a second. And it has satellite communication capabilities, just like you see in the movies. You could actually control it from very, very far away and behind mountains and stuff like that. But that's not something we're currently able to use within the confines of the rules. I'll talk about that a little bit later. It has something called ADS-B in and out that allows it to communicate with other aircraft. And it also has additional radios that we can actually talk through the platform with air traffic control and visual observers on the ground. So, but more importantly, in order to operate this, that's a true team effort. The ARM aerial facility here at PNL operates it. We have people that are aircraft technicians that have gone to school and keep current. We have something called a mission commander, which is like a co-pilot. We have scientists and payload engineers, obviously, and then we have visual observers. These are the people that need to see the ArcticShark with their naked eye at all times, because that's the rules in the national airspace. And then we obviously do the flight operations management at AAF. The actual piloting of the vehicle is done by contractors from Navmar. They're also the manufacturer of the vehicle. So they're called aerial vehicle pilots. And they also have mission commanders in addition to ours, and they obviously have the technical support. We're also using at times pilots from Mississippi State, their mission commanders and their visual observers. And we have also flown, when the ArcticShark was in the shop, so to speak, we've also flown our payload on that Tiger Shark that MSU has in that upper picture. They're both somewhat similar platforms, with the ArcticShark being a variant and being more capable than the Tiger Shark. So the ArcticShark has operated in Rome, New York, in Pendleton, Oregon, and most importantly, I think for science, in Blackwell, Oklahoma. That's where it launches from to do flights over the Southern Great Plains site. The payload, you'll hear much more about that by Fawn May, but in terms of an overview, basically it measures atmospheric thermodynamics, physical, optical, and chemical properties of aerosol particles, trace gas, some limited amount of trace gases. Also does a very thorough job in measuring land surface properties, and is ready to measure cloud droplet size distribution, although have not flown into clouds yet, because that's not something we can do in the National Airspace System currently. That's something we will do once we get into a military, like a restricted area. That's where we hope to fly into clouds, but we haven't done it yet. In terms of publications, we have 3 publications that are out, with a 4th one in preparation, and they showcase data, and some of this you will see today. One is led by Fan, one is led by somebody, Christopher Niedek out of Zhang's group. She's here today, and then one led by Lexi Goldberger. All right, I want to give you a sense on what we have been doing. So this is, as I said, the first time we went over SGP, we actually did that with our payload on MSU's ArcticShark. And so that the red is sort of the area we're allowed in. That's called a certificate of authorization. You get that from the FAA. But you need to stay within line of sight to a visual observer. So we put those visual observer at the airport, and then the 2 yellow stars, and then a red star over that's where the SGP Central facility is. And since you needs to be in visual contact, and the visual observer needs to deconflict any other traffic, so you can't really go too far away from those stars. That's why you kind of end up with these type of patterns. Those patterns with the many lines, these are the patterns for the Altum multispectral imager. So the first time out, we did 15 hours, 7 flights, and altitudes were very restricted. We stayed 2,500 above sea level to 6,000 feet above sea level. You can always subtract 1,000 feet to get to how much that is above ground, because the whole SGP area is 1,000 feet altitude. So that was with the MSU. And then when we went out for the first time, we actually took the ArcticShark out of our SGP. That was in July 2022. We were even more careful and pretty much flew the same flight plan over and over. Did 12.5 hours, 7 flights. The altitude's a very small sliver from 3,000 to 6,000 feet. These data in the archive are in the archive as well. The second time we went out with the ArcticShark was in March 2023. Again, data is all available. We did considerably more, as you can tell, much more detailed pattern. For instance, we flew that much larger camera pattern, the one with the many lines. Did a lot more flying, and are now operating much closer to the ground, 1,600 above sea level, which makes it 600 above ground. That's pretty much the lowest we'll go anywhere. At the FAA limit is 500 over ground, because you cannot be any lower to any people, and you can never really guarantee that there wouldn't be somebody below you. So we're gonna stick with 500, and to be safe, it's like 600 feet above the ground. It could obviously go lower, but that's not within the rules. So yeah, that is that's this campaign here. And then one more here so the big difference to this next one was we actually have 2 different payloads now that we switch back and forth between flights, so that going forward, users can actually choose between 2 type of payloads. And Fawn is going to talk about that as well. Other than that, that campaign was very similar. And that's the one in June 2023. And then so if you take all of them together, that what I just showed, that's sort of the area we have been able to cover with those 3 first campaigns over over SGP using the ground-based visual observers. So for the most recent campaign, we took it a step further and used a chase plane. So that's an aircraft that is a crewed aircraft that is flying behind the ArcticShark and has a visual observer on board and staying within the rules that way. You might think this is crazy, but it's actually not in terms of cost. It's very comparable to use that chase plane with when you compare that to the many ground-based observers you need. Some people also say, well, why don't you just put the payload onto the chase plane? That's not that easy. As you can tell, for instance, from the huge delays we have outfitting our new Challenger 850 aircraft. So it's actually a very cost-effective way of that chase plane gets rented from a company. We actually flew it ourselves. So it's very efficient and allows you to cover a much larger area. You can see now we requested that yellow square and pretty much covered that entire area compared to the blue area we were before. And we also are able to go much higher now. I'll summarize this in this slide here. So in this latest mission that we just did in August, we flew 13 flights with the ArcticShark, 39 hours, and now are able to double the distance from the airport. The area we covered goes from 29 miles to 380 square miles. We go up to 15,400 feet while still be able to fly low. And for the first time now, we are able to take the ArcticShark legally above clouds and are able to operate above and below clouds and can go within 500 feet above or below the cloud. That's the legal limit at this stage. At this point, with all these missions that we have done at SGP, we've really achieved everything that is possible within the current constraints of the FAA rules, the ArcticShark capability, and meteorological conditions. And that's why we're ready for a user facility call. So there will be two calls coming out here in short order. The first one will be for a campaign in FY24 at SGP. We will offer the two swappable payloads that we have. The call will be released in October, and pre-proposals will be due in November. We'll do a feasibility assessment of that, and then abbreviate proposals due in December 2023. And then this decision is made by Sally McFarlane, informed by independent reviewers in January. And I'll show you that in a graphic way as well. It's a little easier to understand. And then we'll do a second call for a campaign in 25, where we will either offer the Bankhead National Forest site in Alabama or the SGP, so users can choose. We'll still do the existing science payloads. We'll release that call in December. And you can see the other dates there, and decision will be made in July 2024. This next figure helps a little bit to visualize this. So the FY24 call is on this timeline here, and then decision made in January, and the user gets to pick one of three slots. Either currently, we're still working on maybe getting an option for in March, but currently either in May, in July, or in September, a user gets to fly the ArcticShark over the Southern Great Plains site. And then the FY25 timeline is here with a decision made in July 25, and then flights in 25. Yeah, that's really, I think, yes, that's my slides. So did any questions come up? Or?
Yeah. Beat, we did have a question in the chat regarding minimum altitude. Patrick is asking, could special permission be obtained for flights under 500 feet, specifically between 250 to 300 feet?
We would have to think about that. I think we have to think about that. So it would really depend on how far away from the airport, and we would have to be absolutely ensured that that there could be never any people. I don't want to promise that, but it's definitely something we can. It's good to bring this up. Thank you.
There's another question in the chat, Beat, if it's possible to use it at the North Slope.
Not for the current series of calls. we're hoping to include the North Slope potentially in calls beyond. So let's say if FY 26 and forward, but not for 24 and not for 25. Sorry, not yet.
Ismail would like to know why. why no North Slope in these two calls?
Yeah, there's a lot of planning that needs to go into this. There's we tend to wanting to do exploratory flights in any new area that we go to, and the North Slope is just logistically a little bit difficult to get there and back, and we're just not quite ready to get there. We're focusing. That's why we're focusing for now on these CONUS sites.
Ismail says thanks, and then Jian Wang has a question if the UAS can sample in clouds.
Yes, you can absolutely sample in clouds, but you cannot currently do that in the National Airspace System. So we will fly. We need to. This can only be done. Well, one way. I don't want to say only, but one way to do it is in a restricted airspace. And that's something we're looking at in terms of exploratory flights in not user driven yet for FY 25, and then see where that takes us. It's absolutely it's my personal dream to actually get into clouds with the ArcticShark. Okay.
We have a couple more questions there. So Jerome would like to know what region around Bankhead National Forest the ArcticShark will be flown or could be flown.
Right. So we haven't done our site visit yet. That we're currently scheduling that for October. I mean, loosely, we're thinking in terms of an overall area to keep the COA similar to a size that we had at SGP. So I'll say roughly 20 by 20 nautical miles is probably sort of a box that we would try to go for. But again, there's a lot of things to look at. There will be areas we're not going to be allowed to fly over, and I mean that's going to. Yeah, so for now, that's the best answer. We're not going to go 3 times as far as we have so far. It's going to be similar to this SGP box that I showed.
And Julie would like to know what's the max data storage transfer capacity during flight.
I let somebody else know that, but well, let me just say, I mean, I guess the current storage and data transfer capacity is given by the instruments that we have now, and not necessarily made. There's no provision yet for guest instruments to let's say need a large capacity of data. So that's probably the best way to just answer it. All right, let's keep going.
So we had 2 more questions. So and then we'll start with the next presentation. But we had a question about finding out more information about the instrument packages available. I will double check the website because it should be on the website.
And Fawn will talk about that in a second.
Yep. And then what's the timeline for in-cloud measurements? Sorry, they might have missed you.
No, that's fine. Yeah, so the most optimistic thing is that we're going to use one of those 3 green slots that you see there to do exploratory flights in a restricted area. And if it all works out magically, then maybe we'll actually be the first time in a cloud in one of those slots, albeit not user driven. And yeah, that's the best answer I can give.
Okay, great. Thank you, Beat. I think.
All right, let me stop sharing.
Yep. On to our next presentation.
I like the questions. All right. And you need to swap. Yeah.
Can you see my slides?
Yes.
Okay, great. So after Beata introduced all the exciting news, and I'm gonna talk about all our middle-sized US data and show you how to get those data through data discovery. So here, just to give you a sense of how we, the 3D flight tracks, how we flew our ArcticShark in August, like this plot colored by the seconds of the flights. So this is on August 27th, we flew up to the 15,400 feet above the sea level and also maintain our lowest lag at 600 feet above the ground. So, and this is with the chase plane, like coordinator together to finish this pattern. Here, just to show you our current capability we have in this slide, you will see the baseline measurements we have include aircraft states such as the positions, their orientation, and we also have some meteorology data that include the temperature, pressure, and we have some minimal gas phase information at 2 Hertz and 1 Hertz. There's a water vapor concentration and the CO2. And the 3D wind can go up to 100 Hertz. And we're working on to get those data archived. You can also find those from the ARMA data discovery by the end of this year. But the rest of the 1 Hertz data or 2 Hertz data are all available now. And this payload also provides some flex measurements. Right now is under the evaluation. And I think later Jason gonna talk about more about these measurements. And for the land surface properties, we have IR thermometer and the autumn camera, which provide surface temperature and the multispectral images at a different wavelengths. And the interesting, for those users interested in aerosol measurements, we have 2 switchable payload. We can do it between the flights. And both payload are gonna share the isokinetic aerosol inlet. It's developed by Misha Pico at PNL. And after those community inlet, this isokinetic inlet, we have 2 packages. One is focused on aerosol physical chemical property. It includes the total number concentration from 7 nanometer up, and the size distribution, which can be merged, combined aerosol size distribution from POPs, MOPC, and the CDP. Here give you all the information of the size range. It's from 135 nanometer can do up to 10 micron. And also we have a single channel tricolor absorption photometer to give you the aerosol light absorption at 3 wavelengths. And during the flight, we have 8 spots sampler and collect some chemical samples for offline chemical analysis. And later on, we have Qi and Swarup going to talk about more about their offline analysis. The other package will focus on the aerosol size distribution. It includes the kind of extend the lower size cutoff to 10 nanometer. And the MSIMs give you an electromobility size, and the POPs and the CBP will continue to give you the same optical size. So that will brought the whole size distribution from 10 nanometer up to 10 micrometer. And here give you just some little bit more information about isokinetic aerosol inlet. And we did a thorough study, and Misha have the report published through the ARMA report. And this inlet has been successfully installed on both platform, ArcticShark and TigerShark. And it aligned with our 5-port gas probe equipped with the airplane. And also this inlet system can dry the air to less than 40% relative humidity. Here just shows a plot to which are used to evaluate the data. And all our aerosol instrument are following the guidance from the World Meteorology Organization and the Global Atmosphere Watch the standards. Here is the payload kind of give you some visual image of all the payload integrated together into the kind of this tower. They have several layers. Top layer, most of the aerosol instrument, the trace gas layer and the pump in the second, and all the computer at the bottom. So the POPs, MCPC, and all MOPC and the STEP at the top, I calibrated before and after each campaign. And also we do the periodical intercomparison during and after fly in the field. Here just to show you some sample data. And with the Autumn camera, we can provide the sample imagery captured through those through this post processing. And here just to give you two examples at the same area, but at a different sample period. One is in November, one is in June. And you can say by combining this high resolution images and also with our weather data, we hope this will provide you some new insight for the model simulation. And later on in this session, Jerry gonna talk about more of this capabilities. So for the offline, we have successfully worked with Qi Zhang's group from UC Davis to develop this chemical composition offline analysis. And it used the micro nebulization and combined it with the general aerosol mass spectrometry to provide a nanogram level particulate matter characterization. And this Qi gonna talk about the recent exciting data. And we currently run each collected sample for each fly, but for as the Qi continue push the detect limiter to the lower end, we can actually provide a more time resolution on those analysis. And also to collaborate with PNL AMSO group, the Swarm group, we also can look at those chemical composition in different way. Here just show two examples. One is use a computer controlled scanning electron microscope. And that tells us a lot of information about the particle molecular level. And then the other one is the time of flight, secondary ion mass spectrometry. This one is a very powerful full surface analysis, can help us to investigate the aerosol particle surface structures, the morphology, and even the chemical information. And the Swarm gonna introduce more later today. So get to how to access the data for the TigerShark. The facility code is called U3. So if you type into if you come to the ARM data discovery and type into the AF U3 or U3, it will bring up this page and show you all the available data. And right now, for the ArcticShark in 2021, because we also fly TBS in 2021, so the TBS data sometimes also show up. And for the ArcticShark, the facility code is called U2. So here just to give you the idea of what it looks like if you search the website, the ARM data discovery. And here I want to try to show one example. Let's say if you're interested in the aerosol size total number concentration by click AF MCPC, it's a mixing condensation particle counter. It will give you the data from both the facilities. And if you click on the more information of that facility, it will give you this figure show this kind of a screenshot shows like a different data level, and also show you all the information. You can click the visualization data to get some quick look of the data. And another thing I want to introduce to you is the AF ArcticShark deployment dashboard. For all the 2023 flight, we have worked with ARM data center to develop this dashboard to record all the flight information. And if you click the view report button, it will bring you to the page like this. And for each of the flight, we try to provide a short description, tell you what we mainly did for each of the flight. And you can click a view and edit a report to know more about each flight, like how long we stay at each altitude, or how many different scenario we observe during that flight. And if you wanted to know more about our US observational data, and we have one paper published, and you're also welcome to contact either me and Beat for more information. Thank you. Any questions?
Thanks, Fawn. I went, so there were a whole bunch of questions coming in already, and I answered many. Let me just go through them real quickly. One that I need your help on, Fawn, is the data currently available including airflow package 1 and 2 from SGP? I said yes, that's correct, right?
Yes.
Okay, thanks, Gannett. Then there was discussion if CDP is an aerosol sensor. I said yes, it can measure large aerosols, and Gannett backed me on that. Thanks, Gannett. Can we only do daytime? That's yes, only daytime. And right, I mean, there's some rules, first light, last light, or there may also be like half an hour before, half an hour after sunrise. So that's answered. We cannot currently nowhere where the FAA controls any, you cannot fly into clouds. That would have to be an area where the FAA has no control, which would be a restricted area. Ultim camera, we fly at 4,000 feet, and Jason, Jerry will talk about the resolution on all that. Yes, we're flying the DMT CDP. Not that we do have a spec fast CDP, and I guess if that were important for some reason, we probably could make that swap fairly easily if that were really, really important. And then there was another final question: can we add our own sensors? At this point, the answer is no. As I said, we're going to fly for the calls coming out. We're flying the existing payloads with some improvements that we will continue to make. But at this stage, we're not open yet for user-provided instruments. But we definitely would make small adjustments, such as the one we just discussed about CDP. We may add a different particle counter. We may add a few things here and there, but it's not a user-provided payload yet. All right, I think I answered everything and kept us on track.
Yeah, great.
Fawn, you want to launch into your next one?
Yeah, Sure. So next, I will just introduce several scientific examples. We collaborated with a different group. And the first one, just to show comparison of the one of the fly we use the AmSims. And those yellow line shows when ArcticShark flew above the SJP site, so they're in the same region. And before and after is either takeoff or close to landing. And you can say on the top figure, there black line just show at the fly altitude of the Arctic shark. And by compare to those up and down, like two size distribution, we can say airborne size distribution from AmSims mirrors the surface-based SMPS measurements, which suggests on that day it's a well-mixed boundary layer. And that day, the boundary layer top is around like 1,800 meter. So we're really exciting to show this capability. And another one is, I talked about we have an aerosol size distribution. We have some chemical composition. We measured by the offline capability use either MNAMS or TOF SIMS. And so the one practice we did is with a different mixing states assumptions, we can calculate or estimate the cloud condensation particle nuclei cloud condensation nuclei concentration, and we plot those like under different conditions, and also compared with the SGP ground value averaged during that fly period. So this just shows us there's the top SIMs provide more important information about the mixing state and the surface properties, which probably suggests agree better with the cone shell structure of the particles we observe on that day. And the other activity we did is to use our aerosol size distribution data and the profiling information to estimate the aerosol extinction coefficient and compare with the Raman LiDAR retrieval. And this one day we have a relatively good agreement, but we also noticed on different day we have a larger variations. So this is ongoing project. We try to help kind of understand each other and also try to say if those in situ measurements will help to improve the retrieval process. So that's all. And I think I will stop sharing and let next people. There any questions?
Okay, there was one more in the chat from Jerome about the max duration and what is the more typical duration and so on and so forth. So I answered that by saying, right now it looks like the absolute max really is about 6.5 hours with the current setup with the chase plane that's pushing it, and it would be less if we start doing lots of profiles. But we can also of course come back and refuel either the chase plane or the ArcticShark and go for 2 flights. So yeah, I think that answers that. It's not going to do 8 hours in one stretch with the payload. So I think 6.5 is really the best we can do.
Yeah, with the current payload.
Yeah. All right. Is there anything for more specific to fawns? Very nice. I think fawn, the next is Swarup, right?
Yeah.
All right. Okay.
You see my screen.
There you go.
Thank you. Hi everyone, this is Sarup China. I'm from Environmental Molecular Science Laboratory. I'm going to share some of the preliminary analysis that we did in the samples collected by the ArcticShark. So what we want to study is that when the aerosol particles or gases emit and we release into the atmosphere, and then they have these processes, chemical aging and other atmospheric process interaction happens, and before reaching into the clouds. So when these processes are very rapid, and we want to understand what is happening at different altitudes where particle dependence. And to do that, what we did is build an impactor particle collection system called STAC. It's a size and time result collection system. This was specifically designed for the armed result balloon system when we started deploying that stack. And then what we did for ArcticShark basically to modify the stack. Basically, we took the heart of the stack. You can see this is the impactor, basically the stack impactor, and put it in an existing aerosol sample, and then collecting samples with the stack. The size ranges for stack is where you can see the ranges from 2.3 to 0.12 micron. So these are 50% cutoff diameter. We also have some other stages as well modified. So that can go up to 70 nanometer, 50% cutoff diameter. So once we collect those samples, we bring those in the lab and do offline analysis. So for this presentation, I'm showing a very specific case study that was done on June 19th. And you can see that on the left panel, there was a normal concentration on the x-axis versus altitude. And it's very interesting case study here. You can see that from 600,000 meter altitude, the particle concentration remains kind of stable, and then it goes down and then goes up again. So you can really see a mixing layer on the altitude. On the right side, you see the flight pattern for that particular flight on 2019. And for this flight, there was total 8 samples were collected. So the 6 points you can see, this is the sample that was when the flight was going to a specific altitude range. And then we had also a profile of 2 ascending and descending profiles flight as well that collected the entire path. So once we bring those samples in the lab, we look under the scanning electron microscope that Pan introduced before. So this is a scanning electron microscopy, but we look at the images in the transmission mode. So you can see if there's an inclusion within the particles. And you can see there's a different kind of particles, but mostly these organics, which you can see. And also we observe some gigantic smooth particles at about 7 millimeter altitude. We see a lot of these crystalline needle-shaped-like particles, talk a little bit more later. But what we do basically, we look at these individual particles, get their morphology, and get once we put the electron beam, we in the X-ray spectrometer, we can get the elemental composition of 1,000 particles. So it automatically detects the particles and then get their composition. And once we get the composition of individual particles, we can make a size distribution of that data and get a chemical composition. So here you can see the size result composition for different altitude, starting from 610 meters to up to almost 1900 meter altitude. For this particular flight, what we observed is a lot of carbonaceous, this green color, the carbon, nitrogen, oxygen containing particles, and also some contribution of the sulfate. Again, I just want to make sure that this is a very preliminary analysis, and we use our standard classification algorithm, but this info needs to be revised a little bit more to go into like a deeper for specific case studies. So one couple of things to note here is that once you see, if you go to the higher altitude, your size distribution is shifting to the lower side, which has a smaller, higher number fraction of smaller particles. And also you can see a higher abundance of this yellow color that are the sulfate particles. We have a high abundance of sulfate, which is not surprising. We expect to have a lot of sulfate particles at higher altitude. The other thing then we started looking into those meteorite shaped particles that we showed in our previous slides. So you can see this is the elemental mapping of the specific particles. So you can get a spatial heterogeneity within the particle. And you can see the needle shape is rich in both potassium and sulfur. And if you look at the other portion of the shell portion, is mostly dominated by carbon disulfide. So it's a mixed particle with the potassium sulfate and manganese. And these particles specific, this potassium sulfate particle was very abundant in between 750 and 1,000 meters. So I believe there was something related to the rate of humidity and dehydration happening that affect this production of this crystalline particles. What else we can do looking into the phase state of the particles. So what the phase means if the particles are solid or semi-solid or liquid state. And the way we inform get an idea about those particles is that when the particles impacted on the substrate by the deformation of the particle shape, you can get an idea about the phase. So if you have a solid light particles, typically they tend to maintain the spherical shape, while with the semi-solid particles, they become like very spherical. While if there's liquid light particles, like the pancake-like structure, which you see in most of the particles here observed at even different altitude. And one of the reasons for that might be there's a high fraction of sulfate amount of individual particles that can have higher abundance of these included particles. So most of them are mixed. So this is we have been doing so far, and I just want to mention what's our plan for this particular set of filters that we have. We have a collaboration with Advanced Light Source, where we have a team plan that is coming actually this month, where we plan to look at these samples, looking at the carbon speciation. So in this with this instrument called Stixon, what you can look actually the functional group level information of the individual particle scale. So you can see if there's a very organics or how mixed with other inorganics or like or soup-like structure like XP2 formation. And the other thing I want to mention briefly that we what we plan to do next also the looking into our high resolution mass spec with the direct analysis method called NanoDesi. So in that we demonstrated this method using some of the samples that was started with the TBS. So it will be this very similar approach. What you can get is that looking into the molecular level information of the organics. And for this particular case, these are sample emitters. So we're going to look at the particles that has a higher concentration, specifically the smaller particles at the lower stages of the impactor. And you can get information, for example, the carbon oxidation state, or then from the molecular composition, you can parameterize the data and get the quality distribution for their phase state composition. So yeah, these are the plans we have. And okay, thank you. And we'll be taking the questions. And we'll see the chat if there's any questions.
Yeah, so there's one for you, Swaroop.
Yeah.
Seems all aerosols are spherical from scanning microscope, which can't be true. Is it a resolution issue?
So it's not spherical from the top view, yes, but you don't see not all the particles are spherical. It's based on the there's a top view, even though there's a pancake-like particles, you see a spherical, right? But you can see there are some non-spherical particles. The resolution we have, I think, is good enough to detect anything above 100 nanometer. If the particles are smaller than 100 nanometer, then yes, that will be the resolution.
Okay, and I think Fawn, you also posted the response. Okay.
Thank you.
Thank you, Swaroop. Okay, then let's go on. Zhang, UC
Okay.
Davis, our guest speaker.
Okay, let me share my screen. Okay, let me project. Okay, can you see it?
Yes.
Okay. Okay, so I'm going to talk about the chemical analysis of aerosol samples obtained from the unmanned the drone. And so this is basically the ArcticShark UAV serves as an excellent platform for collecting aerosol samples from aloft. And the chemical analysis of these samples can offer valuable insights that can complement the measurements at the ground site. And this is the picture that should show here. The bottom graph, the bottom time trace shows the, let me see if I can have the pointer. Okay, so the bottom graph time series come from a ground site aerosol chemical speciation monitor. And the time trends above here are the meteorological and air altitude measurements from the drone. And then this is the flight track. And then the gray bars indicate the PM samples or aerosol samples collected from the ArcticShark. Okay, so however, the analysis of these filter samples that, as indicated, showing in the previous graph, has some major challenges. And that's primarily because of the payload restriction, fairly low air sampling flow rate, limit the amount of PM we can collect during each flight. So this is a rough estimation under the assumption of about 10 microgram per cubic meter ambient PM concentration. You need about 7 hours to collect about 10 microgram of PM. And so this is the motivation for us to develop and apply innovative chemical analysis techniques, specifically trying to aiming for achieving microlabelization, therefore ability to analyze very tiny amount of aerosol samples using aerosol mass spectrometer. So this is a schematic of the methodology that we developed. So the first step is to extract the sample. So we achieved a micro extraction methodology. And then the next step, we designed this fairly simple experimental setup to achieve the microlabelization and stable microlabelization, and the generated aerosol sending to an online high-resolution aerosol mass spectrometer for chemical analysis. So the analysis involved the usage of internal standard, which is a sulfur 34 sulfate isotope, and this allows us to achieve the quantification of the particle amount, particle concentration. And so this is to show here, really through the usage of this internal standard, we can achieve this linear relationship between the AMS measured concentration and the amount of the mass that's being nebulized. So this is a study that performed, I think 2 years ago in November. And then so there are 4 samples collected from the ArcticShark, including 1 filter samples. That's the composite of all these gray bars, so multiple flights. And then there's 3 impactor samples come from the ground. So that was a pilot study we did and trying to validate and evaluate the methodology. And we compared the aerosol composition measured by this microlabelization aerosol mass spectrometry technique versus the real-time measurements at the ground site from the aerosol chemical speciation monitor. And you can see overall the bulk composition that's indicated by these pies shows a fairly good agreements between these 2 methods. And then this is just to demonstrate also we can achieve fairly good quantification, despite some differences between the samples collected from the drone and from the ArcticShark versus the SESM measurement. We can see there's a very good agreement, and also the temporal variation can be captured really well. And then on top of that, because of the using of a high resolution aerosol mass spectrometer, we can acquire the high resolution spectra of the aerosol particles that's collected from the ArcticShark. And this is just to demonstrate the one important application of this data is that we see this more detailed chemistry that can reveal important insights about the sources and the chemical processes of the aerosols. And so this is, for example, we see these kind of bluish color bars that's representing the nitrogen containing compounds, and which are likely to be a combination of organonitrates, amino compounds, amides, etc. So this is that test study has been published. That's primarily to validate the method, and as a result, we were using, as I mentioned, using the composite PM sample. That's over, it's an integrated particle sample collected over 8 flights. Just because we would like to be sure we have sufficient sensitivity. So in the recent study that the drone samples that's provided by FAN, that's coming from this year, we have the duration much smaller. The filter samples collected over much shorter duration. And so these are demonstrated here. And again, bottom shows the time series measured by the SSM. And then this is our AMS measurement. Again, these are preliminary results. We still doing further analysis and the data validation. And what's showing here, the solid bar shows the AMS measurement. The dashed bars shows the SSM measurement. Again, just what we can see here, this is the fractional contribution of the aerosol composition measured by these two techniques agree pretty well. And then this is the analysis of the organic spectra, as I demonstrated as an example earlier, can potentially allow us to capture the temporal variation of the composition. And then through the analysis, such as the positive matrix factorization, we hope to achieve valid, effective source apportionment in order to understand the aerosol sources and processes as well. So just to conclude, we find that we developed this technique, which is pretty effective for analyzing very small amount of aerosol samples collected from the UAV platform. We can obtain useful information, chemical information through this analysis. And then the preliminary analysis of this year's samples demonstrate there's a potential for more detailed chemical information and being obtained, and especially the temporal variation allow us to understand the sources and the processes to a better degree. That's all. Thank you for your attention.
Thank you, G. All right, it's very nice. I don't think there was anything, no new questions. Usually they come like during the next talk. All right, we're gonna go to the next one. Jerry, are you online now? Jerry, are you there? Probably not. Jason, do you want to go then? No, yeah, Jerry says yes. Just can't hear you. Can you hear us?
Yeah, he said he joined a wire phone, and
Okay. Jerry,
yeah,
you're up to give a presentation. You're gonna try to do that by the phone?
I have his slides. I can share if Jerry can hear us.
Yeah, I am. I'll join on my computer here. No audio or video, but do I have audio?
Yes.
Yes.
Okay. Go ahead and share those slides. I appreciate that. Yeah, I had an emergency trip to Seattle, so I.
Okay,
Okay.
we'll make it work, Jerry. Hold on. All right, so font is, okay, and then full screen.
Okay, can you see the slide?
Is that the first slide?
Yes.
All right, first slide's up, Jerry. Maybe you can introduce yourself real quick, Jerry, because people are probably not very familiar with you. Jerry, are you there?
Maybe you can introduce him.
Yeah, but he eventually needs to be able to talk. Jerry, can you not hear us?
I could always go bad if he needs me to jump ahead while he maybe works on this.
Yeah, maybe that's what we need
Okay,
to
yeah,
do. Okay,
let
well,
you
we're gonna
do
switch.
first.
We're gonna switch to Jason will go next. Hopefully we can work this out. Okay. All right, change of topic a little bit, but good stuff too. Swap the view, yep, right.
Okay, so as Fawn and Beat already indicated today, I'll be talking about the measurements of atmospheric thermodynamics and turbulence. We do have a nice suite of instruments we've developed over the years and have flown on both the ArcticShark and the ArcticShark. Really the workhorse behind all this, and you've seen a little bit of the data today, is the Ames 30. This is actually very similar to the instrument we've flown on the G1 for a very long time. About a decade, we flew the Ames 20. This is a version that's really designed for the airspeeds around a UAS aircraft. It does have an inertial measurement unit on board of 100 hertz. That gets your attitude, heading, all the stuff you want to know about an aircraft, roll, pitch, yaw. With that information and the fact that it has a GPS on it measuring location at 100 hertz also, you can recover 3D winds at 100 hertz. The temperature RH percentage, though, are a little bit slower on this particular instrument. The response rate's around a hertz, and I'll show some data here shortly that kind of gives you an idea where that works well and where it doesn't work well. And because of the low, slower response regarding the temperature, we have over the past year done some engineering efforts to improve our measurements of temperature. The one thing we're currently utilizing is this fiber optic. It's doped with a crystal at the end of it that can give you very, very fast response. The vendor was claiming 50 hertz. We are currently not quite seeing that speed, and I'll talk about that here shortly, about what we are seeing and what our path forward with that particular instrument is. And the other one we've flown for a long time is the Lycor 840. This is even flown on the G1 for a bit. It's really been a very stable instrument measuring water vapor at 2 hertz and CO2 concentrations at 2 hertz. And I should state that the Lycor is behind the inlet. Going to that temperature I mentioned, here's performance data for those particular measurements. This is from March 14th. Vertical measurements of temperature for 2 instruments. One is the Ames on the left-hand side here, and the other 2 are showing measurements from the fiber optic sensor that's called OpSens. That's the vendor of that particular instrument. And the far right is actually potential temperature being calculated. What you can see here is this really strange behavior at first if you look at it as you go up in altitude with the Ames, and that's really coming down to the response rate of the temperature measurements within that particular probe. With a change of altitude, it takes time for it to equilibrate with the atmosphere around it, and so you do see this hysteresis effect. That data is still good quality. You just have to realize when you use it, you want to be at a level lag and give it time to equilibrate before use of it. The other sensor is this fiber optic, and you can see that showing no hysteresis as you climb in altitude on these different legs. Again, very, very fast response. And to further indicate how well that's performing, this is potential temperature on that one given day. And because of its fast response to how well it actually performs, you can really see the boundary layer top here as it starts to kick up to higher potential temperatures. You get out of that boundary layer. We found this probe to be very, very useful this past year. This has been flown on flights in March, June, and most recently August. Again, this is just a time series. Kind of showing how the data could potentially look in that kind of view. This is a lot of data on this one particular plot, but you can key in on the red here. This is the potential temperature. This pink here is the aims. You can see some of the lag in the aims as you go up in altitude. You also can see a very, very steady measurement of potential temperature as the aircraft climbs to different altitudes. Very, very good performance on that one. With regards to water vapor, the Lycor 40 is also performing very, very well. This one here, you can again see this nice inversion layer at the beginning of the flight. The color here indicates time of flight. So 0 seconds is takeoff, 14,000 is at the end of that particular flight day. You can see the morning was cold out and there was this dry slot aloft, but throughout the day that mixed away as that moisture moved in and the atmosphere warmed up. This is some work that Susanna Glinke has recently been doing, comparing a radio launch on June 19th with some of our data. You're looking at here on the far left is temperature measurements from both that fast temperature probe and the Ames 30. We got very, very good agreement. I'll show a scatter plot in the next slide that gives you another way of looking at this. But for the vertical reference here, you can see the fast response performing pretty well, agreeing with a lot of the features in the atmosphere. The one here is RH, and you can see it's struggling a bit with the aims, particularly as you change altitude, it kind of hunts around for it a bit. Though this isn't thermodynamics, it is on this plot. You can see wind speed and wind direction. Both are in very good agreement with the balloon. Obviously, there's a little deviations here and there, but for the most part, it's in very, very good agreement. And here is dew point temperature as you go up in the atmosphere, and you can see both are doing pretty well here, but the Lycor is responding really, really quickly as you go up, especially as you get to the drier part of the atmosphere here. On a scatter plot, this shows nicely here. We go back. You can see the fast temperature here comparing to the temperature from the balloon. Very, very nice, right in the 1-to-1 line. Very, very good agreement. Here in the middle is the RH. For the Ames versus the balloon, you can see it's definitely off that 1-to-1, a bit biased. Wind speed is very good agreement, wind direction. And the other thing to look at here is dew point temperature. Again, the light blue line is regression analysis for the fit for the Lycor data. Dark blue is a 1-to-1 between the dew point temperature on the balloon and the measurements here from the instruments. And you can see the Ames is struggling a bit more, where you can see the Lycor is more like a bias. It's just shifted off a little bit in one direction. There is definitely some change in how that Ames performs as you go up in altitude, and not altitude, I have to take that back, but different temperatures itself. There is definitely variation in how far it deviates away from the Ames. Now that's regarding kind of slower measurements in sense like 1 hertz data. Transitioning now into more of analysis of faster measurements, getting into the turbulence aspect of this presentation.
Hey, Jason, hold on. Let's answer this question now.
Yep.
So Ismail keeps asking, are you sure temperatures are at 1 hertz? Yes, they are, but I think you made it very clear that there is this huge lag, that there's a lot of inertia and hysteresis in RH and temperature of Ames, right? It's just not, while it's 1 hertz, it's definitely much slower measurement.
Yeah, Ishmael, I'll give a little more details on that. So in there is a wire sensor, and it is a thermistor, a thin wire. So in theory, that temperature sensor should be responding very quickly, but the vendor stabilizes it by wrapping around a metal post in there, and that gives it rigidity, but you also got that thermal mass that's impacting its response rate. The relative humidity sensor is just a capacity sensor from my understanding, so it does not respond very, very quickly. But again, if you're flying level, it works great. I guess this is kind of the behind this data discussion today, is giving you a little idea where best to use these measurements.
And the RH that it provides is also very slow.
Yeah, it's the capacitance type sensor in there. It's slow. Yeah.
Right.
Um,
And then,
But-
okay, and then can you address the sensor, can the sensor measure vertical component of winds? Yes.
Yeah, I'm going to discuss that here now, Dooley, going into the turbulence side of the discussion here. I'm going to start first with the fast temperature. This work is being done by PCOR, looking at a power spectrum here versus frequency. You know, with dissipation rates of the atmosphere, you would expect this -5 third line. Misha's kind of plotting it down below in that dashed line to help your eye. I've shifted it up here. You can see, the measurements of the temperature as you start to dissipate here, it starts to deviate from that -5 third theoretical line around, 2 or 3 hertz. Really, if you look at it here, this is 3 hertz. This is not what we really wanted to see on this particular instrument. We are working with the vendor to understand why that is. The vendor has promised us 50 hertz, performance from the sensor. But again, we actually look at reality of the atmosphere. We're not seeing that. Misha's also done some work around the sensible heat fluxes, calculating those, and he's just finding those are looking non-physical. So at this point, we have more work to do. And so I would pause any use of this for fast, like turbulence like work. And for that reason, also Misha's held back releasing that fast data. He doesn't want the public to be using it yet till we understand what is happening with it. With that being said, it still does great with, the 1 hertz, 2 hertz type changes climbing in the atmosphere. It does really, really well with that. Just not much faster. To show you, the vertical wind, to get back to what Dooley was talking about, this performs how you expect. This is from the Ames. You can see that -5 third line up here. I've shifted it down to help your eye, and you can see this dissipate the way you would expect as you go to 10 hertz, 20, 30, 40, even 50 at the end. This is that vertical winds. And this is exactly what you expect. And this gives us really good confidence that this is performing the way it should be, and is actually capturing that type of momentum flux and the turbulence in the atmosphere itself. This could be shown too, these plots that Mikhail's put together. Momentum flux here. And before I go further, I should explain this. This plot does take a second to understand what he did. He did do some normalization here. So on the left-hand axis, for every single flight in March, he identified where the boundary layer was. And so he's normalizing the height of the measurement with the boundary layer height in that given day to kind of help your eye. That also helps to pick out the entrainment layer here. So if you're at unity, you're at the top of the boundary layer, is the best way to read this graph. On the x-axis, that's a comparison of the value being measured from the aircraft divided by the measurement being the value of the measurement being made at the SGP site. For measurements that were close to the site, they're kind of shaded in gray. So you can see here that, we are capturing the entrainment pretty well here. The minimum flux, you can see how it decays. You're getting a little bit more momentum here than maybe at the ground site, but not too much. I have a hard time picking out the one-to-one line here, but it's around here. So minimum flux behaving the way you expect. If you look at the variance of the vertical winds, you can kind of see that it peaks about 2/3 of the way up in the atmosphere, kind of that U shape you get. There is a lot of spread in it, though, I will say. We still got to look at that a little bit more, why there's so much spread out here, and some values are quite large compared to the ground site. But the cluster of them, for the most part, is looking very promising. And you can see that variance is still pretty high in that entrainment layer, but pretty quickly goes away as you go higher up in the atmosphere. And the same kind of behavior, TKE and momentum flux are kind of showing what you kind of expect here. With TKE, you're getting up turbulent kinetic energy, you get a lot of energy in this entrainment layer, and then it decays as you go up in the atmosphere. So this is looking really, really good overall. Again, this is still some of the first time we've really dug into this data, but it does give us a lot of hope that we are capturing reasonably good values from this platform when it comes to fluxes and turbulence. Unfortunately, like I said, at this point, we don't have a sensor fast enough to measure water vapor. 2 hertz is not quick enough for this type of analysis. And right now, with the current performance we're seeing of the fast temperature sensor, we're not getting there either to do sensible heat flux. Data are available. Right now, the Ames I have under request. However, Fawn mentioned to me, and she said earlier that they're working on getting that ingested so it's readily available to the public. So that should be out there soon regarding the Ames 3D wind measurements. The water vapors available under AEF H2O identifier. And fast temperature, again, it's still under evaluation for the much faster frequencies. I need to talk with Mikhail about this, but I'm hopeful he'll be willing to release a 1 hertz version of it for the public to use very, very soon. I don't have a date on that, but we will be working on getting that out to everybody. Thank you.
Okay. What I want to do, Jason, is answer that one question there, and then I would like to give people a 5-minute bio break before we go into the last two. Can you address if sensor gets wet, then fluxes can be not reliable?
Correct.
No
Correct.
reason. Yeah.
Yeah, correct, Ishmael. And that's very, very true. And that is the one downside to that when you get into cloud type environments or precept, it doesn't work. The one thing with this platform, for the most part, we are avoiding clouds and precept at this point. But obviously, once we move into cloud research, that could be a problem for us.
Yep.
It would take a little bit for it to dry out.
All right.
Thanks, everyone.
Thank you. 5 minutes from now, we'll do the last two, and you can keep asking questions in the chat.
Jerry, are you there?
Indeed I am.
Okay, yeah, can you say the shared?
I can see that.
Okay,
So
yeah.
sorry.
When everybody back, you're ready to go.
Sounds great.
Thanks, Julie. I do agree with you too. I've been surprised when I saw that. Again, vendors tell you a lot of things. It is nice when you go through and do this validation type work like this and you actually see it come to fruition. So we've had very good luck working with Aventech over the years, though. They've been a very reliable vendor, and that's the one who does fabricate that instrument. They've been good partners.
So the silence is killing me. This is when we need music. I would just wanted to say thank you to everybody for all the questions. We really appreciated all the interactivity and engagement that you've had. So there will be a survey coming your way after the webinar. So sometime today, you'll probably get that in your inboxes. Welcome back, Beat.
Thank you.
I'm going to address Koichi's question real quick here, Beat, before we start.
Yeah.
That is a good question. 1 hertz and 2 hertz. This aircraft is flying at 33 meters per second. So you got to think about the length scales you're capturing at that type of speed. So 1 hertz, you're getting 33 meter length scales. You're not really capturing much of what's going on with the flux of the atmosphere. 2 hertz, similar. You're getting 15 meter resolution. Our goal really is to try to get that 1 meter resolution or better from the sensor. The smaller you get, the more information you get, the more accurate you measure your fluxes. So our goal really is to try to get 20 hertz and faster on these type of measurements.
Thank
Welcome.
you for the question, Koichi. Very good. So let's see, that's good. I think we've answered most. How many people do we still have online, Yolanda?
39.
Okay,
So we're doing
Very
good.
We're doing good. All right. Stalling a little bit because I said 5 minutes. Jerry, are you now hooked up and ready? And
I'm hooked up and ready. Fan is running the slides. Apologize for the
no
challenges.
problem. Okay, Jerry, you want to introduce yourself? Who you are?
Sure, I'm Jerry Tagastead. I'm a geospatial and remote sensing scientist that has been at the lab for 20 some odd years. Started in NSD and I'm in EED now and been working with the ARM program here. I'm the steward of this particular instrument, the mentor. It's just been the last year, so they're relatively new to me, and we'll be talking about mostly the capability, not so much of the data analysis here, but I look forward to it.
All right. Okay, then go ahead. Take it away.
All right. This capability on the ArcticShark came as a surprise to me. I was not involved with the program. Lexi reached out to help with some of the data processing because we do collect many thousands of image frames on every flight, and then there's a process and protocol to go through and correct all those. And so I had a little experience there. What flying is the MicaSense Altum imager. It's been recently updated. It's an off-the-shelf imaging system that has 5 bands in the multispectral. You can see those there in the blue, green, red edge, and near infrared. And as well as one thermal band, which is co-collected. So it's comes in aligned spatially with all the other bands. And importantly, it's also integrated a downwelling light sensor, which you can see on that lower image to the left. We're using that because the mode of operation for this imager is normally on a little quadcopter. Send it up and you're done in 10 minutes. There's some different requirements when you're flying these longer flight lines and the solar angles changing, etc. Speaking of, I'll just point to bottom lower images. The flight crew struggling to try to get a image of the calibration panel, which is normally pretty easy to do when you're flying a quadcopter. You just hold it up. These mid-size UAS, some interesting challenges. Please, next slide. I've been focused primarily, as I said, on the workflow for correcting, bringing in these data, correcting them, and publishing them out in the via the distribution in the ARM .gov sensor or server. The workflow there is shown to the right, but we have this automated in a series of Python scripts. We're using a off-the-shelf program that actually does the co-alignment of the images and creates the elevational data from the stereo pairs, essentially, of the images. But you can see after we have the flights, we get those data down to a specialized machine that ARM has in one of the labs. We connect in there, we do our spectral calibration, which is a routine that we developed on our own, and this required by the fact that we couldn't just hold that sensor over the panel, fly for 10 minutes, hold it over the panel again at the end, and then come up with a calibration factor that it's valid because it's assuming that nothing has changed during that flight in terms of the solar incoming. So we have a special spectral calibration where we're using the irradiance data from that downward light sensor to do the correction of each frame. And then it's pretty standard, and this is where the commercial software comes in, does the geometric correction, does a mosaic, and then the final step is the empirical line fit. I'll note that when they fly this, the flight crews put out calibration tarps of the known reflectance all the way across these bands, and we can utilize those data to do that final tweak. So we have, in the end, I think we can go to the next slide. And I'm being quick because I used up part of my time by not being ready here the last time with my audio.
We're doing fine, Jerry.
Okay, good. to what we're calling science level multispectral products. So pictures are easy, calibrated measurements in the multispectral range are harder. And that's what we've tried to focus on, is how to do that right, such that when you look at an area, whether you're looking at the albedo or the vegetation signature or whatever it may be, or changes between dates, that you're looking at actual changes and not artifacts of some sort of processing. So we result in these science quality images that are co-aligned with thermal. There's a surface elevation image that comes along with the data package out of that processing, which gives you vegetation height and structure and things like that that might be useful and unavailable to the models from standard sources. The resolution that we're currently shooting for is we're resampling the final product to 1 meter, but there was some discussion of the resolution early on. I will say that depending on the height, we could probably get in the 5 to 10 centimeter resolution of the sensor. Now that's at the lowest heights. At the higher elevations, we're still exploring what the capabilities are, and we're also doing some very long flights, which will really exercise our processing routine, as well as the processing computer and distribution of the final data. So we published some of these. I didn't have the DOIs, sorry, on the products that are out there, but suffice it to say they are being posted on the ARM server and are available. With that, I'll take any questions if there are any.
Thank you.
You can always contact us or Jerry if you want to know how to find the data.
Absolutely.
Very good. Thanks, Tom. And last but not least, Hai Long.
Hey, Pat, can you hear me?
Yes.
Share my screen.
And then Jerome is asking for vegetation structure. Does that mean canopy density? Gary, did you hear me?
Yeah, well, depends on what you mean by canopy density. The height of the canopy is resolvable. The different types of vegetation is also probably known. So if you're talking trees versus grasslands versus shrub, you can infer something about that canopy density.
Very good. Anything? That was the last one, I think. Hold on. Yep. Okay. Hai Long.
So just to confirm, can you see the slides in full screen mode?
Yeah, yeah.
Okay, great. All right, thank you, Beat, and thank you all for staying on, and appreciate the opportunity to talk about our atmospheric modeling work using ARM UAS measurements, along with some other ground-based measurements. First of all, I'd like to thank my atmospheric modeling team, which was assembled for the NASA Activate EVS-3 mission, which is also the funding support make this collaboration with our measurement team possible. And also like to thank ARM LASSO team led by Bill Gustafson for providing some helpful help on setting up our model. And also like to thank collaborators from the ARM measurement side, Fan for the UAS analysis, and Damo for ground-based cloud retrievals, and Zihua for chemical analysis. So, today, as an example, I will just talk about the large eddy simulation of aerosol cloud interactions here. So first of all, this slide show the setup of our large eddy simulation using the weather research and forecasting model for understanding aerosol cloud interactions. So the domain, horizontal domain, is 20 by 20 kilometer, and with a horizontal grid spacing of 100 meter. we use doubly periodic boundary conditions. And in the vertical, model top is about 7 kilometers with a stretched vertical resolution, about 30 meter below 3 kilometer, and then stretched to about 75 meter at the model top. So to run the large eddy simulations, you need meteorological profiles and large-scale forcings, and also surface fluxes. So those are, for this example, I'm going to show here is all from the ECMWF reanalysis. But when we for this case, I'm going to show we also evaluated some of the input files, initial data with available observations at the SGP site. For example, the figure on the right-hand side at the bottom showing the surface sensible and latent heat fluxes from ERA 5 and also from some stations near the SGP site. They actually compared very well. Then for model input for aerosol number concentration and cloud properties and other measurements were from the UAS and ARM ground-based retrievals. So the top figure on the right shows the aerosol input is a fitted not normal size modes fitted to the UAS measurement that Fan talked about. The red line shows the final feed input for the model, and also we to simulate the aerosol cloud nucleation, we also need the chemical properties like the kappa. Here for this study, we tested 2 different values based on the chemical analysis I did at EMSL, showing that if there's a surface coating, the kappa value could be dominated by the thin organic layer that has much smaller kappa. So as you already heard that Jason talked about the nice measurement of the turbulence. So here, first of all, we try to evaluate the model. The model simulated clear sky turbulence used the UAS measurement. The top figure on the right-hand side is the vertical velocity frequency distribution. Black lines from UAS and the red is from the LES model results. You see there's a remarkable similarity of the vertical velocity frequency distribution between the model and the UAS. And the bottom 2 figures shows the turbulent kinetic energy, TKE, on the left, and then the vertical velocity variance on the right. Overall, the vertical profiles, they also, they're very similar. And there's one exception is near about 1100 meter height. The model gives a much smaller TKE and W variance. So we think that's because of there's a sharp inversion that wasn't resolved in the initial profile from the reanalysis. But overall, I think the model captured pretty well the clear sky turbulence. So now comes to the results, main results here showing the time series of liquid water path at the top and cloud top height in the middle, and cloud top number concentration at the bottom. And then the SGP side ground-based measurements is in black, and the kappa, smaller kappa value is in red, and larger kappa value is in blue. So overall, if we compare the red and blue lines, the liquid water path and the cloud top are not very sensitive to the hygroscopicity we used in the model, and they both compared very well with the ARM measurements in black. And but if you look at the cloud drop number concentration at the bottom, it's much smaller when kappa is smaller. We don't show here the effective radius. Cloud droplet effective radius is much larger when cloud drop number is smaller. So, but the number with the smaller kappa value, the measurements is closer to the arm measurements, indicating that the measured chemical surface coating is important and also might be treated wrong in most models, which assume well mixed organic and inorganic components. And also we calculated the 12-hour mean cooling due to this different kappa treatment. Over the domain is about 1.2 watts per meter square weaker. Instantaneous 12-hour means that value, but at some point it could be much as high as 10 watts per meter square. So for the last slide, I want to introduce our hierarchical modeling framework that is used to integrate the arm in situ and remote sensing measurements, including the UIS ground-based and some VABs. And we aim to gain process insight into aerosol cloud interactions and also try to narrow the gap between observations and our system models by improving some subgrid scale aerosol cloud parameterizations in large scale models, and also refining ground-based LiDAR retrieval algorithms and other measurement strategies. With that, we'll stop and thank you for your attention. Happy to answer any questions.
Thank you, Hailong. Right, are there questions for Hailong? All right. So, Michelle, I don't know, but is it, we could just spend a few more minutes if people wanted to ask direct questions without having to type. Well, okay, wait, there's 4 more. No, that's good. It's all good. Yeah, do we want, anybody have a question they just want to unmute and ask for any of the presentations?
I don't know if Jerome's question is for models or
which one, the vegetation structure?
Yeah.
Yeah, Jerry addressed that when you were getting ready. So, okay, anybody? Now that you have to unmute, there's no more questions.
There's one about the kappa value.
Okay, yeah, go ahead.
Yeah, just quickly, Fan, please feel free, your chemists feel free to kick in. But the kappa value in the model parameterization of cloud drop activation is one of the variables we need to use for the aerosol activation. So that's why the nucleated cloud droplets, cloud droplet number concentration is sensitive to this value.
Yep.
And what needs to be selected? So mostly we use different aerosol components, their own kappa values, and do a volume mean calculation. The assumption is that they're all well mixed, but seems like based on the measurement, it's not the case.
Right. So I think, Fawn, correct me. I mean, so one way is normally you would fly a CCN instrument, which is a large instrument, which you cannot fly. Well, there are some miniaturizations, but anyway, we don't have one that's small enough to fly on an ArcticShark, and you can measure that kappa, or you do the detailed chemical measurements, and you try to model and provide an estimate of the kappa through the chemical measurements that would tell you how many aerosol particles will end up nucleating into a cloud droplet, which is what HiLong needs to see what clouds will form.
Mhm.
Did I say this right, Fawn?
Yeah.
Uh-huh. All right. Jason, anytime. Okay. Wait. Jason, anytime when sensible flux or surface energy flux could improve.
We're working on it, right? I can say we're working on it. There'll be a big effort next fiscal year, to get this solved.
Yeah.
So.
TJ says, nice talk. Can US activity be collocated with TPS? Probably not, just curious. I think within certain parameters, that's definitely something we do need to look at. I mean, in terms of parameters, it would mean a sufficient distance from the balloon that our safety people would feel comfortable with if the balloon were to become loose from the tether, so that we can't get hit. But I think if we're with the appropriate distances, that could be done in the future. And then Koichi, specific plan to estimate soil moisture. That's for Cherry, I think. Can we get any soil moisture from the spectral information we currently have? We may have lost him.
Yeah, Jerry probably already left. And I think, we briefly talked about that before. With the current capability, we're probably not able to get a soil moisture to the scientific level we're satisfied.
Right. Yeah.
There's a question from Yoon Jae.
That's for you. Go ahead.
Yeah, so we do have 4 size log normal size modes for aerosol input. However, for this specific case, we use the uniform aerosol size distributions. So, but we are thinking of with more ULS measurement and maybe other measurements, we could do more. Can have vertical distribution of different size, vertically different size distributions.
Very good. Okay. Anything else? I want to keep people here. Okay, I see. Oh, thank you for the answer. Yeah, so much is very important. Yeah, I mean, I do know one of the methods obviously is a they're microwave-based methods typically used for that. And I don't know how small those sensors could be. And we'll definitely need to do a little bit of literature review and see what's potentially out there. Thanks for bringing that up. I had a question. Yes.
Yeah, like USGS already deploy one of the sensor for evaluation for soil moisture.
Oh, okay.
But right now, I think the preliminary data shows there's still some big uncertainties for the small sensor on the drones.
Right. Do you know if it's microwave based or something else?
Yeah, it's a microwave based.
Right. Okay. I don't know if I win the lottery. I did have. I mean, I don't know if Jerome is still there. I replied to you, Jerome, is this domain sort of that we're able to cover of 20 nautical miles by 20 nautical miles times 15% gives you regular miles. Do you feel that's reasonable at this for what you would like to do, or what the modeling people or a general process study people want to do?
I would have to look at the bankhead for a site in more detail. Knowing that number, I can go back and look and see what does that really translate into, how things are varying with the vegetation and land use in the area. So it's a starting point. That's just what I need to know.
We did overlay the roughly 20 by 20 with the high scale G1 flight tracks that we have done. And it shows that everything we did over SGP was actually roughly within that. Obviously not these larger flights, what did you call them? Wall flights, but a lot of the stuff that you did during high scale was kind of done in that 20 by 20 thing.
Right.
Yep. So that's good. Any other sort of like yeah, guidance or from anybody else on what they would like to see, and keep in mind it's all a work in progress, and hopefully we'll be doing this for many more years and get more instruments on there, be able to do guest instruments, be able to go to other places, but we just need to go. It's a very slow, deliberate process. There's lots of red tape for us to go to a new site, and it's not that easy. So, but the payoff is good. I think we're creating some nice data sets. Okay. See chat. All right. Jason, okay, so let's thank everybody that spoke. Fawn, you did a lot of this, putting this all together. Thank you very much. Jason, great presentation. Hai Long. She, if you're still on. Who am I forgetting? Jerry, Swaroop. Am I leaving somebody out? I think that's it. And then, okay, there is
Yes,
an,
sir.
Yourself.
oh yeah, myself.
Yeah.
Right.
Yeah,
Glad-
the Bill
okay.
has one more question.
I see that. I'm glad to see the good vertical velocity info. Can we get close enough to cloud base to get a good estimate of cloud base mass flux? Legally, we can get within 500 feet, that's 150 meters above the cloud, or 500 below the cloud. Now, laterally, we have to be a lot away. I think 2,000 feet.
Something like that. It's large.
That's large, but horizontally, it's 500. Is that close enough, Bill? Yeah.
Spoken like a true scientist.
It's a cop out. I actually don't know what we would need, but knowing what's possible is half the battle. So.
Right. Yep.
And obviously, in restricted airspace, we can get closer, right, Bat? That's the thing, right? It opens
Or
up
in.
a lot of, or in restricted airspace, we could get closer to the clouds.
Or
we could.
even inside. Yep.
Or in, right, exactly,
Yeah.
right.
And the bigger is clouds, they're raining and things that brings other issues into play, I'm sure. But
No, we're not going to fly near vigorous clouds anyway. That's just not, it's not going to happen.
We like happy clouds. Okay.
Yeah, we're only doing happy clouds. I mean, Humulus, what's the next stage? Whatever.
you don't
Cumulus
want
or
the nimbus. Yeah.
Yeah, I mean, once they're starting to develop, you gotta leave. Yeah. Okay. Well, Rolanda said this has been the most, well, you could speak for yourself, Rolanda.
I was going to let you do it. I was going to say thank you all. This has been a wonderful webinar, and it's been one of the most interactive and engaged with our participants. So I appreciate all of you for speaking up and asking questions and making this a fun webinar. Oh, and we will be, with the recording, putting it on YouTube and connecting it to the ARM trainings webpage so that you can come back and rewatch anything that you would like to watch, or if you had to step away for a few minutes, come back to those sections that you want to watch again.
All right. Thank you, everybody.
All right.
Have a good
Yeah.
rest of your day.
thank you.
Thank you.
Sure.
Thank you.